Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we're going to be focusing on global radiation. And first, we'll kind of think about the physical properties related to radiation and heat energy, some physical properties. And then we'll move on and really kind of think about it on a system scale, exploring the globe where radiation comes from, how is it stored, how does it interact within our atmosphere and on Earth's surface. So let's begin with the basics, if you will. So the first law of thermodynamics is energy cannot be created or destroyed. It can only change forms. And really, we're going to be focusing on all of these forms that energy exists and changes into throughout today's lecture. And so first, we'll think about conduction. So conduction is the transfer of heat due to the collision of atoms and molecules. And so really think kind of not quite vibration, but think about transferring heat through collision. And so in that way, kind of a vibration. And so here to kind of emphasize different materials conduct heat more or less. Like metal is a very good conductor of heat. That's why we usually use metal pans to cook with. And so metal will conduct heat through collision where you heat one side and it will collide and the atoms and molecules are then literally transferring the heat across that medium, being metal in this case, while other materials are less conductive. And so just appreciate when we scale up to think about Earth and Earth's surface, all of the different properties and materials existing on Earth's surface, including the atmosphere. So there's various different conduction capacities among these types of materials. All right, convection is another incredibly important form of heat transfer, where transfer of heat occurs in a circular motion. And so this is matter that rises and sinks. And really here today and then moving forward in our course, we're going to focus this largely within our atmosphere. And so our atmosphere is matter, has matter, and a medium. And there are large convective cycles within our atmosphere and also smaller ones. And so we'll start to think about some of those large and small cycles today and expand on that moving forward. Then also water, for example, and here kind of showing convection within a pot of water. So we can also apply these within a lake or an ocean. There are large and small convective cycles. And so you have hot air rising and then cooling and then sinking, and that creates heat transfer. Finally, here, the third major form of heat transfer is through radiation. And so this is transfer of heat by electromagnetic radiation. And so this is why it feels hot when you stand in the sun. You're literally receiving that direct radiation directly from the sun. And so that here, another way to kind of think about it is standing near a fire. If you're close to the fire, you can like literally feel that radiation transfer of heat emanating in the form of long-wave radiation being emitted by the fire, and you can feel that radiation being emitted. Same goes for the sun in that case. So those are our three main forms of heat transfer, and we'll kind of integrate those here throughout today's lecture. A term we've already talked about a little bit, but here to define directly, insolation, which is the amount of incoming solar radiations, sun's incoming rays that reach Earth's surface. And so we'll think about this hot object, our sun, emitting electromagnetic radiation in all forms, but largely here in terms of quantity, we think shortwave radiation as a little bit of a review. That radiation passes through space, it reaches the edge of our atmosphere, enters our atmosphere, which has matter, mass, material, and within our atmosphere, that radiation is interacting in various ways, which we'll explore next. But then also when that radiation reaches Earth's surface, it's also interacting with Earth's surface and would interact with different materials, like a forest versus a field versus a building versus water, et cetera, et cetera. So we'll explore that later. So this amount of incoming solar radiation is always constant. The sun is always producing energy, electromagnetic radiation, at a constant rate. While there are some caveats to this in terms of like sunspots and solar flares, largely for our purposes of thinking about the radiation and energy budget on Earth's surface, we're going to think, and very much is true over time, that the sun produces this constant amount of energy. And in fact, it's 1,370 watts per meter squared. And so that's the amount of energy reaching the very edge of our atmosphere at all times, at least when it's in the path of sun's rays. And so then now really today and moving forward, we're going to really think critically about what happens to this radiation, this insolation, which is the amount of incoming solar radiation between the edge of our atmosphere and Earth's surface. And then we're really going to kind of focus on the atmosphere, what happens within the atmosphere, as well as what happens when it does reach Earth's surface. Because as I just mentioned, different materials have different heat transfer properties. And so we'll kind of focus on some of these major different materials and think about the fate of energy, if you will, when it does eventually reach Earth's surface. So now let's begin our journey kind of thinking about these interactions with the atmosphere itself. So what happens to radiation? Does all of the sun's radiation reach Earth's surface? Does this 1,370 watts per meter square just pass directly through the atmosphere and reach Earth's surface without being affected in any way? Well, that would be incorrect. Our atmosphere has mass. We have stuff, literally molecules all around us. And so all of these molecules, the matter, the mass that makes up our atmosphere, are interacting with this incoming solar radiation. And they do so in a few different major ways. Really, it's either reflected or absorbed. And so I'll kind of highlight the difference, subtle difference between scattering and reflection. But the key here, and I have this defined in a future slide, reflection is simply the redirection of energy. Reflection could be redirecting almost backwards the way it came, or scattering really is just subtly where you are redirecting energy and it is perhaps not coming back the way it came, but off to a side angle. And so either way, reflection and scattering do not involve absorption. And so reflection is redirection of energy. There's no net loss. Whereas absorption is when the material like water vapor or methane or carbon dioxide or other material within Earth's atmosphere, even particulates, absorb that energy, they store it for some period of time, and then they re-emit that energy as long wave energy. There's no net loss in terms of the first law of thermodynamics. However, there is a change in form. And so we went from shortwave radiation being emitted by the sun, where some property of Earth's atmosphere, like water vapor, absorbed that shortwave radiation. It stored the shortwave radiation for some period of time and then re-emitted that energy in another form as thermal infrared energy. And so those are the major paths, if you will, of energy within the atmosphere. And so these collectively add up to, or at least reflection and absorption, the indirect paths of energy. And so in a little while, we'll explore like what percentage of solar energy can pass all the way through the atmosphere and reach Earth's surface as direct radiation. Some radiation from the sun does in fact make it all the way through Earth's surface, all the way to the surface as direct radiation in the form of shortwave radiation. And then a proportion of that total, so a proportion of the solar constant, have these indirect paths, and they are either reflected, so it's either redirected without a net loss of energy, or it is kind of this temporary storage where it's being absorbed, stored, and re-emitted, and then that re-emitted energy could in fact make it to Earth's surface at a later point. So let's kind of compare direct and indirect radiation more directly, sorry. Uh, Direct radiation is solar radiation that is absorbed directly by Earth's surface. And so, as this very simple diagram shows, we have the sun, it's a hot object, it's emitting electromagnetic radiation, and it is dominated by high energy shortwave radiation. And some of that radiation does, in fact, make it all the way through Earth's atmosphere, all the way to the surface. And so that is what we refer to as direct radiation. However, a proportion of that solar constant, that amount of energy from the sun, is absorbed. And so this is a form of assimilation. That shortwave radiation is stored within the atmosphere, and then it is re-emitted in another form of energy by a medium being our atmosphere. Again, our atmosphere has mass, it has carbon dioxide, it has methane, it has water vapor, it has many constituents, and some of these and many of them are capable of absorbing and re-emitting energy. And so this is what we call as absorption. And then reflection here in terms of this kind of like simplistic diagram, there is some proportion of this direct radiation that reaches the edge of the atmosphere that is reflected. And so there's actually a proportion of the sun's energy that actually never really even makes it into our atmosphere, or if it does, it's fairly short-lived. It literally is reflected off of something. There's no net loss or change in energy. It is redirected into another direction, and it literally goes off out into space and it never returns. And so some proportion is reflected. And then there's also this proportion that's reflected within the atmosphere, which then may also make it eventually to Earth's surface through kind of more of a tortuous path, if you will. And so reflection is solar radiation being redirected without being absorbed. So think kind of like a mirror, like shining a light on a mirror. It simply bounces off, or a laser to a mirror. And so there's no net storage, there's no transference of energy. It's just a pure redirection. This also occurs on Earth's surface. And so now we've kind of started within the atmosphere. We have the solar constant, we have sun's energy reaching the edge of the atmosphere. And then within our atmosphere, it can either be absorbed or reflected. However, as we mentioned also, some proportion of that energy, direct radiation, reaches all the way to Earth's surface. And then what happens? And this is what we refer to as albedo. It's a way to understand and describe the materials of Earth's surface and their relative capacity to reflect energy. And so the relative amount of reflection by Earth's surface or within the atmosphere itself. We're really going to kind of focus, at least with albedo, and to understand and appreciate this concept, we're going to focus on different Earth materials, like a forest versus blacktop versus water versus snow, etc., to kind of understand this relative amount. It really is 0 to 1 or 0 to 100%. So 1 being high, meaning it reflects everything, 100% reflection, or 0 being 0% reflection, which would then indicate 100% absorption. So we'll practice this a little bit more moving forward. So here, just kind of like this simplistic diagram to kind of better understand scattering and reflection, redirection, and deflection of radiation by atmospheric gas or particulates within the atmosphere. And really, like as I mentioned a few times, if you have incoming radiation coming into Earth's surface, it can be reflected kind of back in the way that it came at this sharp, large angle, or it can just kind of be subtly redirected, and it could kind of bounce and bounce and bounce. And some of this redirection or scattered energy will eventually make it to Earth's surface, while while some of that radiation, other percent, if you will actually be redirected right back out into space and be effectively lost to Earth and its energy budget at that point. So reflection, the solar radiation that is redirected without being absorbed. We've said it many times, but to hear directly define it. So the key being it is not absorbed. Um, then we talked about direct radiation, which is the amount of radiation that actually reaches Earth's surface. And so we have the solar constant, the radiation that reaches the edge of the atmosphere, and then the direct radiation is the amount of that radiation that actually moves all the way through the atmosphere and reaches Earth's surface without being absorbed or redirected. Here, then, indirect radiation is the amount that reaches Earth's surface after it has been scattered, reflected, or absorbed and re-emitted. And so kind of an animation to elaborate or kind of focus on that. So I'm going to go back, just it's a fun animation. And so here, indirect radiation is this proportion of energy. So again, we have solar constant, it reaches the edge of the atmosphere. Some of that radiation makes it all the way through to Earth's surface. That's direct radiation. Some of that radiation is redirected back into space, indicated by this arrow. However, there is a significant or considerable proportion that is redirected within Earth's atmosphere and eventually makes it to Earth's surface. However, it didn't do so in a direct path. It was redirected. And so this again can take forms of being redirected through reflection and scattering, where there was no absorption of energy, and then it eventually took longer, but it eventually makes it to Earth's surface. But there's also this really important part where some of that radiation was absorbed by something like a water vapor molecule, a particulate, carbon dioxide. It then was re-emitted as long wave radiation. So it changed forms, and that radiation does still, in fact, make it to Earth's surface. There's no net loss in energy based upon the first law of thermodynamics. But it did so later and in a different form. And so this is indirect radiation. It's all of the radiation that was either scattered, reflected, or absorbed and re-emitted. So now let's kind of think a little bit more just about conditions and how different weather conditions or even Earth's surface conditions later affect this kind of relative amount of direct versus indirect radiation. So how much radiation reaches Earth's surface on a clear day versus a cloudy day? So we can kind of set up a thought experiment, if you will, that looks something like this. And I encourage you to even pause here or shortly and kind of think about this in your own time, just to kind of appreciate or think critically about how the conditions on Earth here, the atmospheric conditions as either a clear sky or a cloudy sky. And so if we have very cloudy skies where essentially you can't see above the cloud, or there's very little breaks in the clouds versus a very clear day with no clouds in the skies, how did these conditions influence the relative amount of direct and indirect radiation? So how much absorption is occurring within the atmosphere on a clear day versus a cloudy day? How much reflection is occurring within the atmosphere on a clear day versus a cloudy day? And then how much is actually reaching Earth's surface? And again, you can kind of compare this on a clear day versus a cloudy day. And then, this all kind of leads us into thinking, which condition, a clear day or a cloudy day, do you expect more direct radiation reaching Earth's surface? And again, direct radiation is the amount of radiation that was emitted by the sun that reaches Earth's surface without being redirected or absorbed and re-emitted. And so we could kind of take a moment, even pause, and try this for yourself. Kind of really, one's going to be more and one's going to be less. You could go through 1, 2, and 3. You could even kind of think about relative percentages, like maybe there's a lot of one of these forms on a certain day and less on the other day. So go ahead, give it a try. Think about which condition, clear or cloudy, has more absorption or less absorption, which one has more reflection or less reflection, and then which one ultimately do you think has the most direct radiation, where we have the most radiation emitted by the sun directly reaching Earth's surface. All right, so now if you chose to pause, we're going to return and I will focus on the kind of outcomes of this. So on a clear day, we have, again, we have energy, we have the solar constant, we have energy coming in from the top, reaching the edge of Earth's atmosphere, and then what happens within Earth's atmosphere. The take home here is that we have considerably more direct radiation reaching Earth's surface on a clear day. And therefore, we have comparatively less absorption within our atmosphere and comparatively less reflection. And so there is matter and material, there's particulates, there's water vapor, there still is a lot of matter within our atmosphere. And so some proportion of that solar constant, that energy emitted by the sun, is still going to be affected in some way. It's going to be scattered and reflected as well as being absorbed and re-emitted. This will always happen as long as there's mass and matter material within Earth's atmosphere. However, comparatively, and the major take-home really of this is that on a clear day, you have far less absorption and reflection, and you have far more direct radiation reaching Earth's surface. And then kind of conversely here on a cloudy day, you have considerably more absorption by the particulates, by water vapor, by water itself in condensed form. All of these properties are both absorbing as well as reflecting and redirecting sun's energy. And so on a cloudy day, you can have incredible amounts of both absorption and reflection, and you could have substantially less direct radiation reaching Earth's surface, and the radiation that then does eventually reach Earth's surface, you'll have more indirect radiation comparatively. So ultimately, you'll have the most amount of radiation reaching Earth's surface on a clear day. And then of that radiation that eventually does reach Earth's surface, you will have slightly more indirect radiation on a cloudy day because of that redirection, absorption, and re-emission. But here, major take-homes, more direct radiation on a clear day, less direct radiation on a cloudy day. So we'll come back to this graphic and kind of think about each of these Earth materials. So now that we've focused our attention within the atmosphere a little bit, now we're going to kind of change our focus and think about what happens to this radiation when it reaches Earth's surface. So once radiation reaches the surface, it either is absorbed or reflected. And so just a graphic to kind of appreciate that for a moment, but we'll come back to that very shortly. So here now we're going to continue our exploration of heat, energy, and transference, and we're going to think about here now sensible heat and then next latent heat. And so what is sensible heat? Kind of like it sounds, it is and can be sensed or measured by touch or feeling. So it's the quantity of heat held by an object like a pot of water, a rock, or earth that can be sensed by touch or by feeling. The key here is it can be measured with a thermometer. And so this often is how we, as humans, most of us think about heat as energy. We can measure this, we can quantify it. However, there is an incredible amount of energy transferred on Earth and within the atmosphere as well as the Earth's surface and materials due to what is known as latent heat transfer. And so latent heat is the heat that is stored and or released, and then when a substance changes state. And so the energy can be stored when water is in liquid form, it's there and stored. And then when water in the liquid form evaporates, and so we have liquid water evaporating, you have this release of latent heat energy. We cannot measure this with a thermometer, but we can quantify it using equations. And so there is nevertheless this considerable transfer of heat energy due to the storage or release. And so we either absorb energy or we release energy. And so liquid water evaporating is absorbing energy, and then here latent heat is being released. And so how does this work? Like, what does this mean? So let's kind of think maybe a little more directly in terms of like how it influences us. And so convection, so we think about convection, which is the sensible heat transfer. And so we can, again, this convection has everything to do with kind of circular movements of heat where hot then rises and then cools and sinks back down. And so you have these convective cycles of energy on Earth's surface. And so this can happen within the atmosphere. If a certain portion of Earth's atmosphere is heated more vigorously than somewhere else, that atmosphere will begin to rise. And then as it rises, it actually cools and then it has to kind of fall back down. And so our atmosphere have these large and small convective cycles, but so does or do the ocean. And so here we have convective heat transfer within Earth. But now let's kind of compare that. So that could be like we can sensibly measure these heat transfer in these convective loops. However, Earth and including us, we always have these latent heat exchanges. Again, either where energy is being absorbed due to a phase change from solid to liquid, or liquid to solid, or liquid to gas, et cetera, et cetera. There's all this energy being exchanged, but it is not quantifiable or sorry, it's not measurable with a thermometer. And so here, just for an example, the reason we sweat, literally like humans or any organism for that matter, is it is this really effective way to release energy. And so it isn't quantified by a thermometer, but it is quantified in the sense of your body, if you're sweating, has excess heat energy stored in it. That liquid then comes to your surface. And then when water changes state from liquid to gas, you have this release of energy from liquid into gas. And so your body is effectively shedding energy through evaporation. And so the same thing happens on Earth. And so here, just to kind of like pretend Earth is sweating. So anytime you have water near Earth's surface and water then is storing energy. And then when liquid water changes to gas through evaporation, as it does around the world, we have this massive transference of heat energy. However, you can't measure that with a thermometer, but you can nevertheless quantify it. And that is one form, or in this case, latent heat exchange. All right, so let's kind of come back and just focus on albedo and relative amount of reflection versus absorption by Earth's surface materials. And so this graphic kind of shows many different very common Earth surface materials and the albedo value. Remember, albedo is a relative percent between 0 and 1, where 1 is 100%, meaning 100% reflection of solar energy, and then a low value means almost all absorption or relatively more absorption. So to kind of focus on snow for a little bit, there's a reason why. Has anyone ever been outside in the snow and the snow is really fresh and white and it's actually cloudy outside, but yet you still feel like you need to wear sunglasses? Well, that's for me. I have blue eyes and fairly sensitive. And so often when it's snowy outside and it's very white on the ground, and even though it's completely overcast and cloudy, I still feel the need to put some sunglasses on. And that's because that radiation, albeit indirect on days when it's really cloudy, is still reaching the snow and it's reflecting, and actually like fresh snow can reflect up to 95% of incoming radiation. That's pretty incredible, meaning only 5% of what it receives is actually absorbed and most of it is reflective. That also kind of like highlights the insulative properties of snow, where because even though you have you potentially on a given day could have a bunch of radiation making it all the way through, let's think about now a clear winter day, and it reaches the snow surface, Now it's incredibly bright, and so then you might even want really dark glasses or goggles on a sunny day when it's snowy outside, because now you have this incredible amount of direct radiation reaching Earth's surface and reflecting off of the snow and then into Earth's atmosphere. And so it's almost like it's like reflection, it's like a mirror. And so in that case, you as a human on Earth's surface, if you were standing up on top of a mountain, you're getting that direct radiation from the sun, and then it's literally bouncing off the snow and coming back up and hitting you. And so you're potentially almost getting twice as much radiation as when compared to just like standing in a grassy area, for example. Kind of more to the point, they actually make specific glasses called glacier goggles or glacier glasses that are so dark because this can be so incredibly bright and intense from all of that like double whammy, if you will, of radiation, that these glacier goggles will have these like warning labels and says, we do not recommend that you drive a vehicle while wearing glacier goggles because they're so dark, because this is so intensely bright. So anyways, comparing snow to other materials, kind of like the opposite, something like blacktop, so man-made here, asphalt, actually absorbs 90 or 95%. And so the albedo value being like 0.5 or zero point 0.1, and so 5 to 10% reflection, 90 to 95% absorption. That's the reason why blacktop can feel so hot in the summer, is that direct radiation comes down, it hits that blacktop, 90% or more of that energy is absorbed by the blacktop, and then it's re-emitted as long wave radiation. And so kind of like different than standing on the snow in this case, you're standing on blacktop in the middle of the summer on a sunny day, you're getting that direct radiation from the sun that is affecting your body, that direct radiation, and then you're also receiving this incredible amount of emission of long wave radiation coming up from all of that amount of absorption. Many of other kind of natural earth materials or surfaces like a grassland or a forest, or then even within agriculture, have these variable amounts. And while there are no singular like forest versus field, it looks like fields absorb slightly less and reflect slightly more. One thing I kind of want to focus on is just appreciate that over time, as we humans influence how much forest, grassland, etc. exist, and then as we occupy and build things like buildings and roads, we can kind of drastically change these like relative albedo values in an area, which then effectively changes the radiation budget for that area, and you can ultimately affect kind of like daily average surface temperatures, because you're ultimately affecting absorption and then emission of sensible heat in the form of long wave radiation. For a little bit, I kind of want to focus here on water, because water is kind of unique and cool. In the middle of the day, when sun angles are really high and directly overhead, the sun's rays can kind of penetrate into the water column because water is translucent in that way. And you have this like really wide range of albedo of sun or of water, and that has everything to do about these relative angles. And so when angles are high, there's a much more absorption, less reflection. And when sun angles are lower, and so when the sun is setting or different times a year, in the winter for us, in that matter, when the sun just never gets that high over the horizon, water is incredibly reflective. And so water has this very different reaction, if you will, or interaction with sun's energy, all depending on the angle. And so the higher the angle, the more the absorption, and then so the lower the albedo, and then conversely, the lower the sun angle, the higher the albedo and the less absorption, so more reflection. So would you rather sit on blacktop or green grass on a really hot summer day, and why? So maybe just think about it for yourself, even pause the podcast here for a moment. So what do you think? If it was really hot, maybe even muggy outside and really sunny, no sort of shade in sight, would you rather sit on blacktop or on green grass? Well, maybe if you really like the heat, you'd sit on the blacktop, but just kind of case in point, or to kind of think about what this looks like on Earth's surface. This is actually a satellite, so a false color image of temperature of Earth's surface, and this is Lake Michigan, or this is near Chicago, rather, anyways. And so it's just kind of showing Earth materials where all of our buildings and roads are very red, where there's more absorption and then emission of thermal infrared energy, which is this red color. And then anything green and blue is much colder. So forest, grass, water all has a lot more less absorption, and therefore there's less emission of thermal infrared energy. So now kind of exploring this here, thinking about reflection and sun angle. And so the higher the angle, we have seasonal variation. So as the sun is higher overhead, that has less amount of reflection. And as the sun is lower or closer to the horizon, we have more reflection. So that can vary seasonally, where in the middle of the summer, we have high sun angles in the middle of the day. And then in the winter, then there's much lower angles, or at least here in Marquette, Michigan, where the sun really only gets about 20 degrees above the horizon in the middle of the day in the winter. We also can think about it diurnally. So over the course of the day, that sun angle in the middle of the day, it's the highest point the sun will reach. And then by the end of the day, that sun angle is much lower. And so this angle of incidence really having a great effect on the relative amount of reflection by Earth's surface. Okay, so now let's kind of turn our attention and focus on global radiation. And so we'll think about what happens to radiation as it reaches the top of our surface and on a global scale, as mentioned. So here, there's a lot to take in with this graphic, and we're going to kind of break it into specific parts. So here's all of the incoming radiation, and this is the wavelength, and this is the amount of energy. But ultimately, we have all of this incoming shortwave radiation being emitted by the sun, coming down through Earth's atmosphere. And then we have thermal infrared long wave radiation being emitted by Earth. And then that Earth that's emitted, and it's going into our atmosphere and then being later potentially absorbed and re-emitted again. And so previous lecture content is really kind of focused on the short wave versus long wave forms of radiation. There are what are known as absorption bands. Certain forms of energy are absorbed, like ultraviolet radiation, absorbed by ozone, or other forms of shortwave radiation absorbed by water vapor, or CO2, or methane. And so each one of these little gaps here in this diagram shows these absorption bands, and each gap literally is directly tied to one constituent in our atmosphere, like water vapor, or the other one being CO2 and another one being methane, for example. And so these absorption bands happen or are tied to these specific constituents. Other components within our atmosphere then also absorb long wave radiation. And so some of this direct radiation reaches our surface, it's absorbed by the surface, Earth then re-emits that energy, and some of that long wave radiation that's emitted from Earth up then is absorbed again and re-emitted, and it might actually even be re-emitted back down to Earth's surface. So tying in multiple lecture content here, thinking about our variable greenhouse gases, so variable gases that are also greenhouse gases. And so water vapor, carbon dioxide, and methane each are very powerful greenhouse gases capable of absorbing energy, and they're in fact capable of absorbing shortwave as well as long wave energy, storing and re-emitting as long wave energy. And so these gases play this incredible role within the greenhouse effect on Earth and counter radiation. To kind of think about counter radiation, greenhouse gas, perhaps also thinking about now climate change in the sense of some of these concentrations, including carbon dioxide and methane, are continuing to increase at this rapid kind of like rate, or this rapid rate that is unprecedented. So in future lecture topics, we'll talk about how we know these values and concentrations are unprecedented, if you will. But however, I kind of want to turn our attention to think about there's this exacerbated amount of heating, literally like warming of Earth's atmosphere in the high latitude regions, especially in the northern hemisphere. And so this video focuses our attention on what is changing in the Arctic region in the northern hemisphere, and what does that mean potentially for future climate conditions. So take a moment, click on this link and check it out. It literally is one of my all-time favorite YouTube videos. All right, coming back then. Um, Here is net radiation, or what is net radiation? So net radiation is the balance between incoming and outgoing radiation. We've really been talking all about it this whole lecture topic. And so we're now going to kind of think about it in this simplistic box model. We have this incoming radiation as insolation from the sun. Then some of it is either scattered, reflected, or absorbed and re-emitted within the atmosphere. Some of it reaches Earth's surface. Some of it then is either reflected or absorbed and then re-emitted, and we can kind of think about this relative balance. Earlier in this lecture, we focused on comparing a cloudy day versus a clear day and what that meant for direct and indirect forms of radiation and how they differ. You could really do the same thing, or kind of the same thought experiment, thinking about different land cover types like forest versus an urban area, and how those net radiation budgets and balances might look differently based upon differing Earth materials. Also tying or connecting to some kind of previous lecture topic, that angle of incidence is so very important. And I really like this simplistic graphic where the major take-homes, when sun angles are high, meaning the sun is directly or nearly directly overhead, close to 90 degrees, you have more energy received. And so the higher the sun, the closer to 90 degrees, the more energy received. And the lower the sun angle, so when sun is closer to the horizon at like 30 degrees or even 20 degrees, you have much less energy received by Earth's surface, in this graphic depicting it. So imagine holding a flashlight and that flashlight casting that energy, like the sun, directly down onto Earth's surface. That energy is concentrated in this relatively small space, 1 unit of surface area, if you will. Then if you change the sun angle from 90, 45 to 30 here, the same amount of energy, the solar constant, is being emitted by the sun. However, that same energy is now spread out over twice Earth's surface. And so, meaning at any single point in this space, you're receiving less energy per unit area, because that same energy is now being spread out over twice, or even as it gets lower, more of Earth's surface. Then as we think about that on a global scale, so high latitudes, and so areas near either of the poles, never receive direct 90-degree radiation. The sun is never directly overhead of the North Pole. When the North Pole does receive energy, it in fact is at this kind of much lower angle, and so it's spread out more. So high latitudes receive less energy per unit area, as depicted in this graphic here, whereas low latitudes near the equator receive, when the sun is out during the day and overhead, they receive considerably more energy per unit area. So now we're kind of connecting pieces. We're going to think about also seasons and tilts, so tying in some previous lecture content, and kind of think about that on how energy is receiving, or how Earth's surface is receiving energy on a single day, and then kind of comparing different days of the year, and then thinking about ultimately kind of an annual energy budget, how much incoming solar radiation is received at different latitudes. where high latitudes versus low latitudes, again, receiving more or less energy. So tilt matters. And so because we're tilted, the poles would not receive any energy. If we were perfectly up and down and the sun was perpendicular from us, our poles would always be aligned and they would never receive any energy. But we are tilted, and so when northern hemisphere is tilted toward the sun, the North Pole is receiving energy from the sun. But however, a half a year around, and so as Earth revolves around, and then the northern hemisphere is tilted away, you have complete darkness. So during the northern hemisphere winter, the North Pole is receiving zero energy. There is literally zero incoming radiation reaching the North Pole. Annually, if we compare, like if you had a radiometer and you measured incoming radiation at the North Pole over an entire year, what you would see is the equator receives considerably more radiation over the entire year, where the pole receives 40% less insulation when compared to the equator. And so then this really ultimately in the future, we'll think about climates. This then translates into our Earth's major climates, really driven by these latitudinal gradients. But now let's think about on any given day. And so we're going to focus on, and for this question, a 24-hour period. What does it look like? Like, what literally does it look like if you're standing at the North Pole on the summer solstice, so June 21st? First, before we kind of think about energy, like think about if you were standing there and here you're standing, I'm going to pretend I'm standing at the North Pole. And so is the sun directly overhead or is it kind of like lower on the horizon? Well, in fact, yes, it is pretty low on the horizon. At the North Pole on the summer solstice, the sun is above the horizon, and it's in fact above the horizon all day long. And so I'm going to kind of spin around here. And literally, if you were standing there, you could like do a 360, just like I did, and watch the sun go all the way around you. And so the sun is not at a high angle, but a low angle. So there's not a ton of energy. There's not that much energy received at any single minute or period in the day, but it's receiving energy all day long for 24 hours. So that's kind of a unique thing. So do you think there's more or less incoming solar radiation received at the North Pole when compared to the equator on the summer solstice? Well, not meant to be a trick question, and we could actually like literally measure this, and we have as humans in general. And so because of this axial tilt, and because you're receiving 24 hours of direct in or not direct, but of you're receiving 24 hours of incoming solar radiation at the North Pole. Actually, there's more total radiation over a 24-hour period received at the North Pole on June 21st than the equator. It seems crazy, but it's true. But again, remember that angle is so important. So it's not to say that it's warmer at the North Pole in the middle of the summer than it is at the equator, because those angles are pretty low. However, you have twice the amount of time approximately that the sun is up. For 24 hours, you're receiving a little bit of energy. So kind of cool. So then this really kind of does translate into our very latitudinally driven climate divisions. In a future lecture topic in this course, we'll explore climates and then ultimately also biomes as they're related later. But just appreciate, and as we most of us can, the warmest climates are near the equator. And as you move away from the equator, largely speaking, you then go from equatorial, tropical, subtropical into the mid-latitudes. And then as you go north and north and north, you're reaching this subarctic into the polar regions. And so this average insolation over a 24-hour period largely driving these major like climate divisions here. Again, even though the North Pole is receiving more energy on the summer solstice over a 24-hour period versus the equator, remember there's also several months of darkness. And so over the course of the year, the North Pole receiving again 40% less insolation total when compared to the equator. And so daily insolation really to kind of like connect and tie things together here again. Angle of incidence is so very important. Like, how high is the sun in the sky? Is it really high, close to 90? You're receiving lots of energy, or is it lower on the horizon? You're receiving much less energy per unit area. And then time, and so duration. How long was the sun up? Was it low energy received for 24 hours, like the North Pole or the South Pole during the winter solstice? And then, or was it really high in the sky and up for 12 hours? And so kind of balancing angle of incidence and duration is important when kind of thinking about radiation budgets on Earth's surface. And so here in Marquette, Michigan at 46.5 degrees on June 21st, we have relatively high sun altitudes. It's not 90, but it's close to 70. And we have considerably long days, so much longer than 12 hours. So it's pretty darn warm here in Marquette, Michigan on June 21st, typically. And so just directly on insolation, assuming it's clear outside in Marquette, there's quite a bit of insolation. We have quite a bit of insolation received by Earth's surface on June 21st in Marquette, Michigan, because the sun angle is relatively high and we have relatively long days. Here's a graph that I really like, and there's 4 major insolation plots here. So we're going to think January, February, March, so January through December, and now we're going to have these major latitudinal zones. And so what I would like you to do is I would like you to match the insolation plot here with the latitude. So now how do we begin? And so here's insolation 0, and then to 600 on the y-axis, and then our time on the x-axis here. And so what place on Earth for several months doesn't receive any sunlight? Well, the answer would be the North Pole. And so the only graph here that you see that's receiving 0 insolation is this yellow plot. And so you could actually then match 90 with the yellow plot. And then I encourage you to pause the podcast and kind of work through this on your own, thinking about which one here's 90, and then it could be going down 60, 30, 0. And so also kind of thinking about at the equator, you receive the most insolation here in March and September. And so on the equinoxes at the equator is when the sun, the subsolar point, is directly above. And so here you see this kind of bimodal aspect of the blue curve, and really also showing that near the equator, you receive very high amounts of energy consistently throughout the year. And so even though there's more insolation received by the North Pole, and in fact by many other northerly latitudes, and on the summer solstice here, even though the equator is receiving less, there's this huge portion of the year that the equator receives quite a bit of insolation, where the rest of the northern hemisphere receives very little. And so here to kind of fill it out, but I do here encourage you to practice this graphic, as it might be a good use of something like a matching question in the future. So to tie it all together, or to kind of like summarize it into the most important aspects, it's really important to consider both the angle of incidence, high energy with high altitudes or angles, so closer to 90, and then also the duration. So with that, Dr. VG is signing off.